This video is about heat and temperature, as you can obviously see. Topics that are pretty familiar to all of us, but I think you'll see as we get going, there's a lot more to this than you might think. So the first question is indicative of that. What is heat? This question everybody understands, at least the words in it. There's no words that you don't understand, but actually defining it can be kind of difficult because we have to define this in terms that will separate heat energy from every other form of energy that we're going to talk about in this class. So it turns out the best way to do this is to say that heat is the energy that is transferred between objects because of a difference in their temperature. Now, sometimes it's useful to look at what is implied by a definition, and sometimes that's obvious, but we still may not see it if we don't look. First of all, this says that heat energy is transferred. Why? Because two objects have different temperatures. And there's actually a direction that heat flows. It always flows from hot to cold, or from high temperatures to cooler temperatures, warmer temperatures to cooler temperatures. There's never been a time in the history of the universe when heat energy has spontaneously flowed from a colder object into a warmer object. It simply doesn't happen. That would be like putting an ice cube on the countertop and making the ice cube cause the countertop to increase its temperature or to heat up. That's not possible. It's not that it's not possible because the ice cube does not have any heat. We'll talk about that in a minute. There is heat in the ice cube. It's just that it has a lower temperature than the countertop does. Therefore, the heat will flow into the object that has a cooler temperature, always, always. At least that's the spontaneous direction of flow. We can get it to go the other way, but it takes some doing. It takes some work. So energy is transferred because there's a difference in temperature, which also means the implication is if two objects do not have different temperatures, aka if they have the same temperature, there will be no energy transferred between them, no heat energy transferred between them. So heat flows from hot to cold until what? When does heat flow stop? Well, we've already said up here that if there's no difference in temperature, energy is not going to get transferred. So that's when heat flow stops, when the temperature of both objects is equal. So for instance, imagine that I have just a block of some kind of metal, doesn't matter what it is, but let's actually focus the camera. How about that? Camera's not focusing. That's better. Let's say I have a block of metal. Let's say this is aluminum, and it's the same type of metal and the same mass of metal as another block that has a temperature of 50 degrees. Same type, same mass. Because of what we just said, we know that heat will flow from the hot to the cold. It doesn't go the other way. We might be able to get it to go the other way, but it takes work to get there. On its own, it flows into the cooler object. So heat, Q, is what we're going to use for heat. Heat is leaving the 100-degree block. It is entering the 50-degree block. The 50-degree block is receiving or absorbing heat. And so what we get from that is that we can see that the temperature of the warmer block will decrease because it's losing heat. We can see that the temperature of the cooler block will increase because it's gaining heat. And because these two objects are the same mass and are made of the same material, more than likely we are going to end up at a temperature of 75 degrees because this one will decrease, 75 degrees here because the 50 will increase. In other words, they both kind of meet in the middle. We'll end up at the same temperature. Again, they're only at the same exact temperature right in the middle because they're both have the same mass and they're made of the same material. But even if they're different materials, they will both end up at thermal equilibrium. And at this point, there's no more heat exchange, no more heat flow between the two because there's no difference in temperature. There's no hot, there's no cold, there's no higher or lower temperature. It may not be at 75. It depends on what type of material it is, which one has more mass. If there's more mass over here, we might end up at a higher temperature. It just depends. But the point is they will reach thermal equilibrium at some point, and at that point, no more heat is going to be exchanged between the two. So this situation, when the temperature of both objects is equal, you need to know this is called thermal equilibrium. It's a very important phrase, an important term that you need to know. Thermal equilibrium is what happens when two objects, regardless of their initial temperatures, there's going to be heat exchange between them from the hot one to the cold one until they both reach the same temperature. It's called thermal equilibrium. All right, so let's go ahead and talk about temperature now that we're getting to that point, because another thing that a lot of people confuse is they think that heat and temperature are sort of the same thing. And they're not really. They're related, but there's some very, very key differences. So let's talk about what temperature is. So let's remember, heat is energy. Energy that can be transferred. It's a thing, it's a substance that can be transferred from one object to another, specifically from a warmer object to a colder object. But temperature, on the other hand, is not the same thing. Temperature is a measure of the average kinetic energy of the molecules of a substance. When you think about the word average here, let me get a little pen. Average, a lot of people don't understand the meaning of that term. I think I need a different color. How about yellow? The meaning of the word average, a lot of people think it means approximately or about. That's not what it means. If I take the average grade on a particular test in this class, that doesn't mean everybody made that grade. And that doesn't mean everybody made close to that grade. If the average is 70, I might have some 40s. Let's look at a graph here. I might have some 40s, and I might have a couple of hundreds, right? But if the average is 70, what that means is the average is the grade that is mathematically in the middle approximately of this bell curve of grades that I might get. That means the majority of the grades can be found right here, and right in the middle of those, that is the concept of the mathematical average. So if we're talking about average, that's what the term means. And then kinetic energy. We've just got through talking about kinetic energy. You know that kinetic energy is the energy of motion. So that means kinetic energy, average kinetic energy of the molecules of a substance. That means what are the molecules doing? Well, they're moving around. And the fact, I'm sorry that the illustration just went away. I recorded this on 2 different days. The molecules are moving around, and the fact that we're talking about average kinetic energy means that some of the molecules have a lower kinetic energy, some have a higher kinetic energy, and that average is what's going to be right in the middle. That's just a measure of the kinetic energy of the molecules. The next point on the notes talks about absolute zero. So as we heat an object up, that increases the movement of the molecules. It increases their kinetic energy, increases their temperature. And as we cool an object down, that means the molecules are going to slow down. It's going to decrease their kinetic energy. And if we cool it down more, they'll slow down even more. And the next logical question is there a point where the molecules ever stop? And the answer is theoretically yes, and that point is called absolute zero. But there can be no temperature below absolute zero, because at this point, all molecular motion does come to a stop. It has ceased. There can be no temperature below absolute zero, because you can't go slower than zero. Now, the reality is, and if you were here in class, you watched the video that I showed called making things colder, making stuff colder. The reality is it is impossible to actually reach absolute zero. Scientists have gotten very, very, very close, within a few billionths of a degree Kelvin. They've gotten very close to absolute zero, but it's impossible because of actually what's called the Second Law of Thermodynamics, which is technically what we've already talked about, which is that, it was right here, heat always flows from hot to cold. So if you actually reach absolute zero, if you are successful in doing that, that means the molecules have zero energy. That's the lowest possible amount of energy you could have. And anything around that is going to inevitably have more energy than that. And as soon as you reach absolute zero, the molecules around wherever you're talking about, whatever point is at absolute zero, they're going to want to very quickly give energy to that object, and it's so that's the reason why it's impossible to reach absolute zero. There's always energy in molecules. There's always energy somewhere. There's no way to reach absolute zero. All right, so since we're talking about temperature, I actually want to go in the notes that you have down to the bottom of the page where it says temperature scales, and let's talk about these 3 scales real quick. So here we go. Fahrenheit, Celsius, and Kelvin. BP stands for boiling point, FP stands for freezing point, and specifically, this is for water. This is for water. These three scales, you might remember, probably Fahrenheit is the most familiar to you, and the freezing point of water for Fahrenheit is not 22, 32 degrees Fahrenheit. That's the temperature you watch for when the weatherman's talking, because you might get out of school if there's precip and temperatures are below that. Boiling point, many people don't remember because it's random. It seems random. 212 Fahrenheit is boiling point of water. Same point, but on the Celsius scale it looks different. Celsius is much prettier. 0 Celsius is freezing. 100 Celsius is boiling. And on the Kelvin scale, many don't remember this either. 273 Kelvin is freezing point of water, and 373 Kelvin is the boiling point of water. Now, as we look at these three temperature scales, you might notice several things. The first thing that you might notice is that both of these scales seem to be somewhat random, but these numbers are very nice. Almost like as if maybe somebody set it up intentionally that way. And they actually did. The Celsius scale was intentionally set up to reflect water. When it was set up, the idea was that since we use water a lot, it would be easy and it would make sense to make the freezing point of water 0 Celsius, the boiling point of water 100 Celsius, and therefore the scale was set off of those 2 points, and everything else falls into line there. You might also notice there are 100 degrees of difference between those 2 points, and just for kicks, you might need to know that 37 degrees Celsius, that's your body temperature. 98 degrees, 98.6 Fahrenheit is 37 Celsius. Speaking of 100, you might also notice the same thing about Kelvin. 273 to 373, there's 100 degrees of separation there as well, which means this. The Kelvin scale and the Celsius scale are the exact same scale. It's just that the Kelvin scale is jacked up about 273 degrees. But basically what happened here is it's the same degree of separation, the exact same scale. And we'll talk about the Kelvin scale in just a minute. It's the Fahrenheit scale that should look the most goofy to you. The most goofy because it looks the most random. 32 and 212 don't seem to have anything to do with each other. There are not 100 degrees of separation here. There's actually 180 degrees. So the first thing I want you to realize is that the Fahrenheit scale is a fundamentally different scale. I shouldn't even have the same picture of a thermometer here. The amount of difference from 1 degree to the next on the Fahrenheit scale is about half of what the difference is from 1 degree to the next on the Celsius scale. Practically speaking, that means this. If the weatherman comes on here in the United States and says that the temperature is going to rise 10 degrees during the day, from 50 up to 60, right? 50 degrees Celsius to 60 degrees Celsius. That's not really that big of a temperature change. You may not even need to plan for that in terms of what you're wearing that day. But on the Celsius scale, it's quite different. If the weatherman comes on and says that the temperature is going to rise, I don't know how to write this. Let's just write it over here. Celsius, if we're going to go from, let's say, 25 degrees to 35 degrees, that's actually a bigger deal. It's 10 degrees, but it's much more difference in terms of temperature. 25 degrees Celsius is more like about 76, 77. That's a pretty comfortable temperature for us as humans. But if we're going up to 35 degrees Celsius, you remember 37 Celsius is your body temperature. We're talking about close to a 95 degree day there. So that's a bigger warm up. These are fundamentally different scales. The Fahrenheit scale, one of the legends was that the Fahrenheit scale was set up based on body temperature, and that the one that set it up wanted body temperature to be 100 degrees, but didn't get it quite right. You and I now know that body temperature is actually 98.6. So the entire scale is random. When you set it up that way, the freezing point of water just happens to be 32. The boiling point just happens to be 212. It is random, and for that reason, I don't know why we still use it in this country, but we're really not going to be concerned about the Fahrenheit scale much here in this class. It's the Celsius and the Kelvin scale that I really want you to focus on. Now, Kelvin. Usually when I ask students which one of these scales looks the most random, they won't pick Fahrenheit. And the reason is because they're used to it. They think Kelvin looks the most random because the numbers are so big. You've never heard a weatherman say the high today is going to be 300. But the Kelvin scale is interesting because it's jacked up 273 degrees, and there's a reason for that. So here's what Kelvin did. Remember that when we came up here at the top of the notes, we said temperature is, and I didn't write it in mine, but hopefully it's written in yours, temperature is a measure of the average kinetic energy of the molecules, right? So if temperature is supposed to reflect kinetic energy, I told you, remember, I told you that energy, E-N-E-R-G-Y, energy cannot be negative. Energy cannot be negative. Have you seen negative Fahrenheit temperatures? Yes, you have. Have you seen negative Celsius temperatures? Of course you have. They have negative temperatures. And so if temperature is going to reflect the average kinetic energy of the molecules, actually Fahrenheit and Celsius are the ones that make the least sense, because we can't have negative energy. If we're talking about that, then really this 0 point is fairly arbitrary. It's just for water, but water is just one substance that we deal with. But if we're going to talk about temperature in general, it makes sense to make the 0 point the absolute 0 point, where there is no kinetic energy. And that's exactly what Lord Kelvin did. He said, hey, let's make this to where the 0 point actually reflects absolute 0. That's what he based his scale off of. Absolute 0 happens to be negative 273 degrees Celsius, 273.15 to be exact. But 273 degrees below this point is where all molecular motion ceases. But we still have energy all within here, so it makes no sense to make those numbers negative. So Lord Kelvin set this point at 0, and we go up from positive there. There are no negative Kelvin temperatures. All right, so you need to know, the only thing you really need to know is how to convert between Celsius and Kelvin. And the temperature, the equation is super simple. You can see the difference between those two. It's the same scale. You just add 273 to go to Kelvin, or you subtract 273 to go to Celsius. That's it. So the equation is K equals C plus 273. All right. So that means if you have a Kelvin temperature and you want Celsius, so this one over here, we would plug our Kelvin temperature in here, and then we subtract 273 to get Celsius. If we have Celsius temperatures, we plug the Celsius temperature in for the C, and we just add 273, and you got Kelvin. 0 plus 273 is 273 Kelvin. 100 plus 273 is 373 Kelvin. And negative 270 plus 273 is actually 3 Kelvin. Now we're going to subtract 273 on this side. Put the number in here. 100 minus 273 is negative 173 Celsius. 0 minus 273 is negative 273 Celsius. And 373 minus 273 is 100 degrees Celsius. That's the boiling point of water. So you'll need to know how to convert between Celsius and Kelvin.